Hi, it's Robin. In a recent video, we looked at a few aspects of Robotron 2084, which was designed by Eugene Jarvis, and I mentioned he also worked on the famous arcade game Defender. That prompted viewer Steve Tardif to comment that he'd like to see a video about the C64 port of Defender by AtariSoft, which I have right here. Steve mentions an interesting thing that happens if you hit the restore key while your ship is exploding. We'll look at that in a moment. And his question is it a bug or is it intended? And just to clarify, Eugene Jarvis programmed the original arcade game along with Samuel Dicker, according to Moby Games, but today we're looking at the C64 version of Defender, which was developed by AtariSoft way back in 1983, when they often didn't credit their programmers. However, GameBase 64 says the C64 version was programmed by Joe Simko. Unfortunately, I don't have the original Defender cartridge, but I did find a cartridge image online and was able to flash it onto my Easy Flash 3. Just try the C64 Defender a bit here. It's actually pretty good, especially for 1983. Oh, well, that wasn't so good. But Defender was always remarkable for all the firepower, just like Robotron and actually most Williams games. I'm doing terribly here. There's the various people down on the ground. I don't know why they just stand around on this mountain, but looks like they're standing on a mountain. Scrolling is pretty nice. It's a little bit quirky, but overall, I think it's an excellent port. Good audio, too. Oh, gotta save that guy. Oh, I missed him. He's dead. Oh. Another one. If they manage to take a human all the way up to the top, it turns into these kind of mutants, these extra power aliens. Oh. Well, he survived. I didn't catch him. Probably got to be able to catch one. Well, there's mutant. Killed him. Or it. What? Alright, one more. Okay, let's let a lander, I think they're called, an alien, pick up a human. There's one. There. And drop him back down on the ground. There, you're safe. Alright. Anyway, pretty tough game. But so's the arcade. But this really is an excellent port, especially when the Commodore 64 was maybe not even a year old. And many of the tricks and techniques weren't figured out yet. Okay, so here's the bug. When I'll just die here. Watch that explosion. Do you see how big that explosion gets? I'll do it one more time. Deliberately crash. Boom! Big explosion. Okay, this time I'm going to hit restore. When the explosion happens, it's at its maximum. Okay, so there's actually almost two bugs here. You see how the explosion sprite is stuck on the screen. That's pretty funny. Or I find that amusing. Okay, but then if you start a game, this is the really neat part. Your ship is supersized, but actually everything is supersized. Look, the humans are... the aliens, everything's so giant. Oh. But then, when you die, it goes back to regular size. So you only get that mode for a little while, the supersize mode. Let's do that one more time. Just so you can see the large size mode a little bit longer. It looks so cool. I love how the aliens look. Huge pixels. I think the accuracy is a little off, but the shot. Oh, I want to rescue a supersized human. They're like so big that they like pull the ship down. Oh, okay, there. I'm going to save you, giant human. Okay, shake around funny. There. Okay. Okay, so what's going on here? I'm just going to exit back to BASIC. So this game is making use of the feature of the Commodore 64 to expand the sprites. They can be expanded independently in the X and the Y direction. Let's just make a really quick basic program to explain this. 53269 will turn on the sprites, or turn on one sprite. Poke 2040, 13 will set the sprite 0, the first sprite's sprite pointer, to slot or number or definition 13. Line 20, we're going to poke 53248, 150. That is setting the sprite's X position to 150. And the next register is 53249. And we'll also set the Y position of the sprite to 150. And then finally, we're just going to do a for loop for I equals 0 to 63. And we're going to poke 832 plus I, 255. So I didn't put a space there. Actually, we don't have to do 63. I'm just going to do 62, 0 to 62. At 63 positions, a sprite definition is 3 bytes wide, or 24 bits wide, and 21 rows tall. So that's a total of 3 times 21 is 63 bytes to define a sprite. So we're just doing a next loop. 255 is the maximum value. So this is just going to make a solid square on the screen. I'm going to run this, and you should see the square drawn onto the screen. There. Now, it just took a while for the sprite to appear because that was BASIC poking all 63 numbers in. So the top left 8 pixels is in position 832. If I put a 0 in there, see how that little corner came off? I could do the middle byte. There. I can put it back with 255. Of course, you could put any value in there. I'm just doing 0, 255 to make it really obvious. Okay, so we did 832, and if I do 3 bytes below that, 832 plus 3 is 835. There. And if we do 838, we've taken that whole corner off there. Okay, well, I'll just run the program again, and there, it's replaced those pixels. Okay, so that's the normal square, 24 by 21 pixels. I mean, I'm calling it a square. You can call it a rectangle if you prefer. Now, this register, 53277, normally there's a 0 in there. If I put a 1 in there, watch the sprite. There, it became twice as wide. So it's gone from 24 pixels to 48 pixels, but it's actually just doubled each pixel. So you don't have double the resolution, you have double the size, but the resolution's the same. And we can see that by, again, poking 832 with 0. And you see a bigger chunk has come off here now. It's now wider than 8 pixels. It's 16 pixels that's missing. And in addition to 53277, which is the X expand, 53271 to tell sprite 0 to expand in the Y direction. So you can see how big a single sprite can get. And once it's being rendered, kind of the power of the VIC-II sprites, that whole block can move basically instantly by just changing a single register. 53249 is the Y position. I'll set to 100. Currently it's 150. So it should move up 50 pixels. And there it is. And you see it's actually on top of the text. If I change the cursor color, see I can move the cursor under it. And now if I move it up out the top. So the sprites are rendered on their own layer on top of the text. Or there's another bit they can actually render the sprite under the text. And we can put it back where it was. And you'll see the text didn't disappear. Nothing needed to be done to restore the text under the sprite where in the old location. It was there all along. You just couldn't see it because the sprite was drawn on top automatically by the hardware. Now, if we go into the Super Snapshot monitor, you can see that I have this Defender.CRT image on my micro IEC drive. This is exactly the same file that I used to flash the Easy Flash cartridge. Okay, and thanks to patron David Rock for confirming that his original AtariSoft Defender cartridge from 1983 does have this same bug. He played it on his real Commodore 64 and even took a screenshot for us. So, thanks, David. So, what's going on with the huge sprites in Defender? Well, I suspect that is a bug. When you die and that explosion animation happens, that the game, the code, is expanding the explosion sprite for that final stage. It's extra big. And when you hit restore, the game resets, but it never clears that sprite register, that hardware expand, and just leaves it on. And then you can play with the sprites expanded until you die. Then the code finally expands and then resets those sprite expansion registers. Okay, so how to figure this out? We can examine the Defender cartridge in the machine language monitor here. I did a bit of this in the Robotron episode. A cartridge image, one of these CRT files, is not actually a native Commodore 64 program file. It was originally created for emulators, and it's only been more recently that things like the Easy Flash 3 or the Kung Fu Flash or an Ultimate 1541 can make use of these so that you can use a cartridge image on real hardware. But we can still look at it here. So last time I just loaded the Defender cartridge image directly and it loaded into memory at location 3643. And the reason for that is because the first bytes of a cartridge image are 4336. Those are PETSCII characters. If we look at memory starting at 3641, just 2 bytes before, you can see that there's actually text here. It has a couple symbols and then 4 cartridge. So if we put those same bytes, 3643, actually in reverse order, 4336, because the 6502 always does low byte, high byte order. So if we just put that load address back into memory and press return. Oh, it doesn't refresh at the side. We gotta fix that someday. There we go. And I just dumped memory again. And you see that now with these bytes 4336 in, it now says C64 cartridge. The first 50 hex bytes of a cartridge image are actually a header file. So that's 80 decimal bytes. So these first 10 lines here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These 80 bytes from the cursor up are the cartridge header. So we've restored these 2 bytes, but it's a binary file, a Commodore 64 program file. The first 2 bytes of the file are interpreted as a load address, a 16-bit load address telling the file where it should load into memory. When you load a binary file into the Commodore 64, you lose those first 2 bytes in a sense, but you do get told, at least in Super Snapshot Monitor, what the bytes are in the reverse order, so you can put them in for yourself. This is where the file actually loaded, starting with the 3rd byte that was interpreted as the actual data. So you can see a CRT file starts with the text C64 cartridge and has quite a few other bytes. I actually don't know what all of them do. There's this one that says chip, and some of the rest is the configuration, where in memory the cartridge should go, and there's also some bytes to handle special memory mapper, as they might be called on the NES, or ways of handling cartridges that are bigger than the regular 16 kilobyte maximum. And there's also a couple different locations where cartridges map into memory. That's also expressed here. And then the actual cartridge image, the actual ROM, if it was just a raw binary, it starts here 80 bytes later. And this is as far as the Commodore 64 is concerned, this is the header at this location. Now, on this cartridge, it should actually be at 8000 hex. In the previous Robotron episode, I just loaded it here in memory where it defaults. But I've since figured out how to load it into the correct spot in memory. So instead, if we load Defender.crt from device 8, if we load it to 7FB2, this is 78 decimal bytes earlier than its actual correct location of 8000 hex. That is the actual cartridge payload, the ROM, not the CRT header. I told you it was 80 bytes. 2 of them get lost as a load address. So if we load at 78 bytes earlier, then the payload should end up at exactly 8000 hex where we want it. Okay, so I'm loading. It still reports that was being loaded to 3643, but we overrode that with this address. And the way we can verify, this is a 16K cartridge, so it should end at exactly C1000, or actually it ends at BFFF, 1 byte earlier, but it's sort of tradition on Commodore machines to report back the next available byte after what was loaded. And one more thing we should do is just memory location 1 defaults to 37 hex. If we change that to 34, that'll hide the basic ROM so we can see a contiguous 16K of RAM where the cartridge image is loaded. Okay, so all that. Now we can finally look at memory at location 8000. This is the cartridge image, and this is that header I was talking about for the C64. The first 2 bytes are 16-bit pointer to the code that should be run when the C64 boots. So that's 8009, which is right nearby, right there. And the next 2 bytes are also 16-bit pointer when you tap restore, and that's also pointed to 8009. And then the next 5 bytes here, if you change to lowercase, you can look at the side, it says CBM, Commodore Business Machines, and then the number 8 and the number 0. Presumably that 80, I guess it could stand for the year 1980, but I think it really stands for 8000 page 80. So that 5-byte signature, CBM80, indicates that this is an auto-booting cartridge. If you changed any of these bytes, it wouldn't automatically boot. So we know the code starts at 8009, so let's look at it. Disassemble 8009. Okay, so this is the code that executes when the game starts up. So it loads the accumulator 0 and then stores that in D016, which is a VIC configuration register. Then it calls a number of Commodore 64 kernel calls. FF84 is called IO init. So I'll just show a little reference from the Commodore 64 Programmer's Reference Guide, a brief description of what they do. But that initializes the input-output devices. The next one is called RAM-TAS, which initializes RAM and actually tests RAM as well, and also the tape buffer and screen. This next one is called restore, which restores the default I/O vectors. And then finally, it calls cint, which initializes the screen editor and the video chip. So it's actually funny. At first glance, this makes me think that the bug should not happen because this routine at FF81 sets the sprite expansion registers to 0, shrinking the sprites or making them the default small size. So actually, it doesn't make much sense. And when you hit restore, this code should be run because that vector at 8002 also points to 8009. So whether you hit restore or power cycle, it should go through and clear the VIC. But obviously that's not working. So let's just continue a bit further. This clears interrupts, sets interrupt, clears interrupt disable, set interrupt disable. I don't know why both of those are there. There is some funny code here. You can tell in 1983, no programmer was experienced on the Commodore 64, and not all that many were even great at 6502 code, never mind the Commodore 64, all the quirks that its hardware and all the challenges that its hardware introduces. There's some funny code here, but this is no disrespect to the programmer. He did an amazing job. Like I said, especially for 1983, when there were so few resources around. A lot of the code, you could tell programmers were just frustrated. They're just trying to get their job done. And you just experiment, try to work around bugs and strange behavior. Okay, so some 0-page initialization here. That's fine. Just a loop to clear some 0-page. Just the last 32 bytes, it seems. And then just setting the screen color to 0. Initializing some more VIC registers. Oh, and here is something interesting. 0318 and 0319, this is the NMI vector. So when you hit the restore key, it's actually going to go to this address. It's like it overrides. And what address does it go to? 801B. So if we just look back up here, once this code runs, hitting restore will actually start code execution here at 801B, the set interrupt disable, and it will skip all these initializations. I think that's actually the problem. So is this a deliberate behavior or is it a bug? Well, I lean towards bug, but I guess it's possible that the programmer is deliberately skipping this just to make that kind of a fun Easter egg. I don't know though. I think the reason to set the NMI vector to point here instead of this is that these actually take a while to run, particularly RAM tasks. That RAM test takes at least a few seconds. That's when you turn on the Commodore 64 before you get the blue screen. You do have to wait a few seconds before the cursor arrives. And maybe when you're playing a game and the user hits restore, maybe the programmer didn't want to have to wait for that, seemed bad, or maybe just himself, he was testing and he was sick of waiting. So he deliberately pointed the NMI vector to here to skip all this slowish initialization for his own faster testing. But if so, then that maybe is what caused the bug. So we could point this back all the way to the beginning to 8009 or to 800E. But I'll let you know, I actually experimented with this and I didn't like that big pause if you jump back further. So it actually seems to be sufficient to just jump back and only initialize the VIC, and conveniently that's the last in this list. So that would just mean that we change the 1B into a 17 right here. So how to test this? Well, we can save it back to the SD, but there's an extra step. Because I load the cartridge image into the incorrect location, it's correct for reading the code, but it's incorrect as far as the file system is concerned. So the first thing we need to do is save it back to device 8. And we have to save from that same 7FB2 that we did the override on. And we have to save to the end to C1000 hex, C000. Okay, so we have our cartridge image saved, but it has a problem. The load address, that is 7FB2, or actually B2 7F, have been saved into this file, and those 2 bytes are wrong. Instead of that PETSCI string reading C64 cartridge, it's going to be that gibberish, and it is not a correct cartridge image. I don't think it'll even flash with that problem. Actually, I haven't tested that, but it's not right anyway. I think an emulator would certainly have a problem with that. Okay, so how to fix that? Well, this is what I just realized recently. So if I go back into Super Snapshot, I'm just going to reset here. I think I might have crashed it with all that. Okay, so this file called LA, it's actually short for load address. Now, this is a program that came on the Commodore 1541 disk drive. I think I showed this ages ago. So if you're looking for this program, search online for the 1541 test demo, and on it is a file called load space address. I just called it LA here just for short. Okay, and it asks you disk unit NR, so device 8. And this is such an old program, I think that it supported 2 drive units within a single device. Now we enter the program name, and that was def2.crt. And it thinks for a moment, and it tells you the current load address is 7FB2. Do you want to change it? Yes. And now the new address we want it to be is 13891 decimal, which it shows in hex is 3643, and that's the PETSCI for C6, or well, 6C in that order. And do you want to write out the new load address? Yes. You just hit return. Okay, and it says the load address is changed. Change another program? No. Okay, so now we've fixed our cartridge image. By the way, this does work on a micro IEC only when the file's inside of a D64. This load address program does some very direct block writes. I don't know if I can find them here, but yeah, here in this area, line 430, 440, it's actually doing a direct block write into a sector, and it's assuming that the disk directory is on track 18 and writing directly into a 1541 file structure. So if you're in a native folder, which I use most of the time on a micro IEC, it's not going to work because the disk structure is so different. But inside a D64 file, it does match the same, I guess, disk geometry as a 1541. Anyway, that's an interesting program that you might want to play around with yourself. Okay, let's just go back into the Easy Flash now and go into P for Easy Prog. And now, menu, write a cartridge to flash. And we're going to write it to slot 5. And we're going to do that new Defender2.cartridge. And are you sure? Yes. And let's call that Defender Fix. Congratulations. Okay, now we reset, and it's appeared in slot E, Defender Fix. And it's starting up. And there we go, Defender, and let's test it, see if it's fixed now. Okay, game seems to work fine. Crash. There, okay, I reset during, or I hit restore, and you see that the sprite didn't stay on the screen, so we fixed kind of both bugs at once. Or, well, we haven't seen. Let's start the game. Okay, our giant sprites are gone. I'm actually realizing now that this is kind of a stupid thing to fix because that bug is so harmless and fun. It's actually really cool. Should almost do a fix where it's in giant size all the time. Anybody want to do that? Okay, let's try one more time. Crash. There. And it's gone, and it should be normal size here. There we go. Let's play some more of this. That was actually while I was working on this video that I noticed another bug in Defender. I don't know if it's visible yet, but oh, there. Look at the top right of the radar. Well, the white frame of the radar. Look at the top right corner. Can you see that it's looking a little bit funny? There, I think. Oh, there. It's even changed more. That top right corner of the white frame in the radar area at the top is getting corrupted. I don't know why nobody's ever... I've never seen anybody say this before. I've never noticed it just until this week, or actually just the last day or two. And it's gone all bad. So that is something I think I'm going to look into, and it will probably turn into another video. Oh. I saved you, Steve. Well, there, it's corrupted even differently. So anyway, that's something I'm going to look at. That will probably be a video I make first for my patrons. Thank you to all my patrons that support me in all this. It's a lot of fun. And that video will eventually just get released publicly. But I usually make a video every month for my patrons at the exclusive video tier. And they've agreed that after, well, actually 6 months we had agreed on, but it's more like a year later, I actually just released them publicly to everybody. But those videos are often extra nerdy, so if you like that and are able to support what I'm doing, then that is available. Oh, even more corruption there. Okay, so thanks very much to Steve for pointing out this funny bug. You know what? Let's do it. I shouldn't have fixed it. It's just too fun. Here we go. Woohoo! Jumbo Defender. I think the collision's a little bit off. When they're supersized, they actually get longer, and it kind of throws off the X and the Y a little bit. Oh. Oh yeah, so that's always a bug. Even the way the sprites end up on the title screen, that's a bug no matter what. Even if you don't time it with the explosion, if you just do it anytime. So we fixed that. Well, that's kind of a fun bug too. Another harmless one. Okay, thanks to Steve for bringing this up. I had a lot of fun doing this, even if I don't know if the results were worth it. Thanks to my patrons for their support. Thank you for watching, and we'll talk to you next time.